Welcome to module 3 of this course. In this module we will learn basic Boolean theorems. So, from module 2 we will do a few more theorems, and I will also introduce you to the concept of binary numbers. So, let us start with De Morgan's theorem. This is something that you must have seen even in set theory, and this is a very useful theorem to know, and you will see it used in several places. So, De Morgan's theorem basically says that if you have n terms of the form, let us say x1 or x2 or x3 so on up to xn, and if you take the complement of that, so that is what you see in the topmost line here, the complement of x1 or x2 so on up to xn, it is the same as x1 complement and x2 complement and so on up to xn complement. Similarly, the dual of that is if you take and of x1, x2 so on up to xn, and if you take the complement, it is the same as the logical OR of x1 bar plus x2 bar plus so on up to xn bar. So, these two you can imagine this one, for instance, if you substitute plus with union and bar with complement and with intersection, you have your set theory. In set theory you must have learned De Morgan's theorem. So, remember, you have to keep this in mind. If I have two terms of the form x and y, and if I have x and y, if I take the complement of that, it is not the same as the and of the complements. So, complement of the and is not the same as and of the complements. Similarly, complement of the or is not the same as logical OR of the complements. So, keep this in mind, because this is a common and usual mistake that people do. So, keep this in mind, however. So, let us look at a few basic proof techniques. This will come in quite handy. So, we have seen Boolean algebra, we used a bit of manipulations in the last module. We will see a few more of these things, because these things come in handy when you design circuits later. So, we will deal with algebra for some more time before we jump into circuits. So, let us start with the first one here. So, I have several such examples that follow. So, let us start with this: x plus y and z is x plus y and x plus z. So, this is actually the distributivity property, but let us see how to prove something like this. So, in the last module I showed how to prove some of these things using truth tables explicitly, but I want to be able to do this just using algebra, because truth table is laborious and you have to be very careful with all the zeros and ones and so on. Let us see if we can do it with basic algebraic techniques and the rules that we know already. So, let us start with this x plus y and x plus z. Right. So, I start with the right hand side. You can rewrite it as x and x plus x or z, or y and x or z, because you have these two terms and you have these two terms. In some sense it is like expanding the expression which you do in regular algebra. So, now you have x and x plus z, you can write it as x and x or x and z. So, essentially you are taking the product into the terms here. So, that gives you 4 terms here, and if you look at these 3 terms here, there is x which is common in all of these. So, you can rewrite it as x and, so this gives you 1, this gives you z, this gives you y. So, 1 or z or y, and you have y and z which we keep as it is. So, we know that 1 plus any variable or any expression for that matter is actually 1. So, in this case z plus y is an expression. So, 1 or z or y is actually 1. So, we have that here, and finally x and 1 is x itself. So, this is the same as what we have in the left hand side. So, hence this is correct. So, the key thing that we did was here, this is fairly like what we do with regular algebra. So, if you have sum of 2 variables and sum of 2 variables and so on, expanding up to here is probably straightforward, and taking a common term out for and is probably also straightforward. So, the only thing is we have 1 plus z plus y, which simplifies to 1, because this is Boolean logic. So, 1 or z or y is 1. So, this is a fairly straightforward example, and this is much more easier than all the tables than other things that I did earlier. Let us look at a slightly different examples to see what all the different Boolean techniques that you need to know. So I want to be able to show x or y is x, right. So this is actually called absorption rule. X or x and y is x. So let us see how to prove this. Again we start from the, in this case, the left hand side. So one usual technique is try and introduce your term. In this case x is ANDed with 1, sometimes you OR it with 0. So here we want to simplify x or x and y. So if you introduce a term and 1, it does not change the value of the expression. Now once you do this, then you have x which is common to both the terms, so you can take x out. So this expression here is the same as x and 1 plus y or 1 or y. So 1 or y we know is 1, so x and 1 is x. So in this proof what we have used is we have introduced a constant here. So we know that x and 1 is x. So if I give you this one, you would easily write it as x, but sometimes it is useful to go and take something like x here and write it as x and 1. So in this case we can see that it brings x as a common term between these two. Let us see another example here. X and y plus y and z plus x complement and z is the same as x and y plus x and z. So what we have is we have these two terms which appear as it is on the right side, and magically one term seems to vanish. So this is what we are going to show. So this is actually so this is a slightly tricky thing, and this is called the consensus theorem, by the way. So x and y plus y and z plus x bar and z is the same as x and y or x bar and z. So let us see how to start with this. So you have this expression here. So the first thing I am doing is I am taking a this term and ANDing 1 with that. So that is correct because 1 and any term is the same as the term itself. So here I have 1 and yz is the same as yz itself. Then I take this 1 and use the previous technique. I introduce a constant, but I am replacing the constant with the expression here. So earlier I used the constant and I took something out in common. Here I am replacing 1 and I am introducing a function. So we know that x plus x complement is 1. So I did that here, and once you have this, I can separate this term and this term. So I have a product here and I have a sum x or x complement. What I am going to do is I am going to take this out. So y and z and x, and similarly y and z and x bar here. So this and that gives this term here, and now we have these two terms which you can group and these two terms which you can group. So there are common things here. You can see that there is x and y here, there is x and y here. So 1 plus z is the expression which comes from these two. Similarly we see that there is x bar z which is common to this term and this term. So we can take that out and we have y or 1. We know that 1 or z is 1 and y or 1 is 1. So it simplifies to xy and xy or x bar and z. So what happens is this term vanishes and you have xy or x bar and z. So in this example what we have done is we have introduced a constant here and we have introduced a function in terms of the constant. Usually we do it the other way around. If I give you the expression x or x complement, I would expect you to write 1, but sometimes it is useful to take 1 and expand it to a function. So this is a bit of this takes a bit of work to understand and appreciate. It's not easy to come up with something like this in the first go. I don't expect you to do it right from the beginning. So in this case I know that I want to get rid of yz, so I have to do some manipulation in that term, right. So I could have started here, I could have started here, it could be any of those, but I started with the middle term because I want to get rid of that term, and when I wanted to get rid of that, so it's a y and z. So it's natural to put a 1 there and expand it in terms of something that is there on both the left side and right side. So if you look at the left side there is x and right side has x, left side as y, right side as z. So the reason why I wrote x plus x complement here is it looks like there is some function of x which is here and some function of x which is here. So there is x bar here and x here, so I rewrote it as x plus x bar, and then the rest of the steps follow. So this is not something that I expect you to do right in the beginning, but it's good to know some of these tricks so that you can employ them later. Let's look at another proof. So we have x and y, or x and y and z, or y and z. So the LHS is this expression. This is another common trick that can come in very handy at times. So I am going to take this term here x and y and z and make a copy of that. Why can I do that? I can do that because I know that from the single variable theorems x plus x is x, which means even if I have n copies of x all or together is the same as the term x itself. So if you take the term x and y and z, even if I make multiple copies of those, it is the same as one term itself. In this case we are doing the other way around, we take one term and then we make multiple copies of that, in this case 2 copies of it. And once we do that, we can see that x and y is common to these two terms and y and z is common to these two terms, and this will let us simplify things. So x and y and 1 or z, that's, so this 1 or z goes away, x or 1 goes away, so it gives us x and y plus y and z, and y is common between these two terms, I can write it as y and x plus z. So in this example we introduced a copy of this term x and y and z, and we got to y and x plus z. So there is a much simpler way to do this, you go and think about that, but I wanted to show this example so that you know this particular technique, that in Boolean algebra it is okay to copy terms like this. So if you do this in regular algebra, if I give you x plus a, you cannot go and write it as x plus a plus a. So this is not true for all values of a. However, in Boolean algebra, if I give you x plus a, it is okay to go and write it as x plus a, because you have a plus a is a, we know that already. So let us look at a few exercises. This is something that I want you to do later, so I am not going to teach this, but I suggest that you go and prove this later. So we have the absorption laws, the combining laws, and the De Morgan's laws. So I suggest that you prove it either using Boolean algebraic techniques or at least using truth tables. Once you get comfortable with truth tables, maybe you can move to algebraic techniques, but it gets easy as you go along. De Morgan's law, of course, you can prove it with Venn diagrams also, but typically we avoid proving with diagrams when we do Boolean algebra, because doing it with a few variables is okay. If it goes beyond a few variables, it gets very complicated to do Venn diagrams. But I give this as an exercise to you, go and do this. So let us go back to Boolean functions. So we looked at this circuit yesterday where we have a power supply and a light, and we have two switches x1, x2 in parallel and x3 which is in series. And if I give you such a switch, we argued that either x1 or x2 should be on and x3 must be on definitely for the light to glow. If you want to write this expression, write this as an expression, so you have let us say f is the expression for whether light is on or off. So f is 1 if the light is on, f is 0 if the light is off. If you want to be able to write expressions for these, so let us go back to what I said in English, either x1 or x2 must be on. So we know that the expression, the way to write that is x1 or x2, and because of the series connection between this circuit and this circuit here, we need and x3 on, right. So if x3 is off, we know that light cannot turn on, so we have and x3. So you can see the parentheses also, so that it shows how things are grouped. So now I am going to write it as a Boolean expression, instead of using the word or and I am going to use the symbols that I introduced in the previous module. So x1 or x2 is x1 plus x2, and is replaced by a dot, so x1 plus x2 and x3, right. So if you want a circuit out of this, we know that x1 or x2, you have an OR gate, you put x1 and x2 as the two inputs, the output will be x1 or x2, and x3 here is ANDed with this term here, so we put an AND gate and add these two terms here. So this is supposed to give us the expression that we need. So if I we can mentally simulate it also. Let us say these are both 0 and let us say this is 1, which means both these switches are off and this is turned on. So if I put a 0 here and a 0 here, this will be a 0 here because 0 or 0 is 0, and 0 with a 1 here, 0 and 1 will be a 0, so the lamp will not turn on. However, if I have one of them to be a 1 here, let us say I have one of them to be a 1, then the OR output of OR will be a 1. However, I still need x3 to be 1 so that the light turns on. So you can also mentally simulate and check, given a circuit, whether it is trying to do what you want to do or not. So let us look at a slightly different problem now. This is a design problem. So this is a common problem if you have a stairway or a staircase and you have two switches. This is something that you probably have in your homes. So you have a switch in the, let us say in the ground floor, and you have a light that you want to turn on for the staircase. Either you can turn it on from the ground floor or from the first floor. So this is a two-way switch. This is something that you probably have in your homes, right. So we want to be able to design a circuit which takes care of that. So what we want to do is we have two switches that are there. We want that to be connected to a logic circuit in such a way that if both the switches are off or on, the light is off. If one of them is on and the other one is off, the light is on. So this is fairly straightforward. So you might see this in staircases, you also see that in reading lamps and so on. So sometimes you have a light by the bedside and you want to turn on or off the tube light by the switch that you have in the bedside. So this is a common thing that we have at houses. So let us see how to think about this. If both the switches are off or on, the light is off. If one of them is on and one of them is off, the light is on. So we want to be able to think in terms of expressions for these, or so we will start with the notion of a truth table for this. So what we have is, we have this expression if both the switches are off. So I am going to assume that there are two switches X and Y, and I want to be able to design the logic for L. Let us see how to go about writing a table for this. If both the switches are off or on, so let us see all the possibilities that X and Y can take. 0 0, 0 1, 1 0 and 1 1 are the four possibilities for X and Y, right. And what we want is, when both of them are off, the light should be off. So that is this row. When both the switches are off, the light must be off. When both the switches are on, the light must be off, right. So this takes care of the first bullet. Let us look at the second constraint. If one of them is on, the other one is off. That is true for both of these rows. One of them is on, the other one is off. In that case, I want the output to be 1 or the lamp to glow. So this is the truth table that we want. Sometimes you are given a problem in, so the real world problems are always in English descriptions. You want to be able to take that and move it to tables. So that is what we have done now. We have a truth table for this function. So this is the same table as what I did on paper, and this is the first step. Let us say I want to realize a circuit which does that. So I have a truth table, this does not give you a circuit, so I want to be able to get a circuit which does that. So the first thing I want to be able to do is, I want to write a Boolean expression for this. So let us see how to write a Boolean expression for something like this. So what we do is, we start from the right side. So we look at the output, we look at all the places where we have a 1. So there are two rows, this row and this row here, which have a 1, and what we are going to do is, wherever there is a 1, we go and look at the left side. So the left side is either we have 0 1 or 1 0, right. So if you want to read it in English, lamp is on when either X is on and Y is off, or when X is off and Y is on. So let us look at the first condition. Either X is on can be checked by checking the switch on X, and Y is off. Either that condition must be true, or X must be off and Y must be on, right. So this term comes from this row here. So, x is on and y is off, and this term comes from this row here, x is off and y is on. So, now from a truth table we have an expression, and once we have an expression we can do several things. So, the first thing is, if I want, once I have an expression, I may want to realize a circuit out of this, right. So, let us go and try and realize a circuit out of this. We have the expression x and y complement or x complement and y. I want to realize a circuit for this. Let us see how to realize a circuit for x and y complement first. X and y complement. So, if I give you y as an input, I can't use y directly, I want y complement. I know that y complement can come if I have a y and if I stick an inverter there. So, this will be y complement. So, this is x and y complement. Similarly, if I take x, take its complement and AND it with y, this gives me x complement and y. So, this takes care of the two terms, but we still have this logical OR in between. I can do that by putting an OR gate here. So, this is the circuit which can realize the functionality that we needed. So, what we have is the logic network that we need, or the circuit that we need, is essentially a slightly redrawn version of this. So, in the paper I had two different x inputs and two different y inputs. Here I am showing that it is actually coming from the same input. So, x, this line goes as x and this comes as complement, and if you notice there is a filled circle here. In electrical circuits we use that to denote branches, right. So, you probably know that from your basic electric circuits, that when you have a dot on a line it means that you are branching. So, x is branching here and branching here, this line comes as x complement, this line goes as x. Similarly, for y here, this line goes as y, this line goes as y complement. So, this one is for x and y bar, this is for y and x bar, and that is L. And this is such a common thing that we have a symbol for it by itself. This is called the XOR gate. So, the XOR stands for exclusive OR, EXOR or XOR stands for exclusive OR. Exclusive OR means if I have two inputs, exactly one of them must be 1, the other one must be 0. So, previously we looked at OR, or the logical OR, which is also called inclusive OR. So, it allowed the case where if both the inputs are 1, the output is 1, whereas in XOR if both the inputs are 1, the output is 0. So, exclusive OR essentially says exclusively one of the inputs must be 1, which automatically means the other input is 0. So, this what you want for this two-way staircase or this bedside lamp, bedside switch for a tube light is essentially an XOR gate. It is as simple as that. Let us look at another design problem. Design a circuit which realizes the following truth table. So, we have two inputs x1 and x2 and we have four outputs, sorry we have one output f of x1 x2. There are four combinations that x1 and x2 can take. The first thing I want you to think about is what is the way in which we can write this expression down. So, I have written the same thing on paper here. So, we have 4 terms 0 0 0 1 1 0 1 1, there are 4 combinations of x1 x2 and I have f. So, just like what I said earlier, if I want to write a Boolean expression for this, we want to be able to look at all the ones here and look at the corresponding terms on the left side and combine them properly. So, let us start with the row here. In this row there is a 1, and what is the combination of x1 x2 that gives a 1 there? x1 must be off and x2 must be off, correct. So, that gives you 0 0 here. Then let us get to this row. So, this gives you the case where x1 must be off and x2 must be on, and finally this row says x1 must be on and x2 must be on, right. So, we have 3 ones here, these 3 ones correspond to these 3 terms here. So, one thing you have to do is, we know that either if this input is given or if this input is given or if this input is given, the output must be 1. So, we stick a plus in between these terms. So that is the Boolean expression that we need. So the Boolean expression for f is x1 bar and x2 bar, or x1 bar and x2, or x1 x2. So eyeballing the truth table and being able to write a Boolean expression like this is very useful. So sometimes you will be given the Boolean expression, you have to write the truth table, but more often than not coming up with the truth table is fairly easy to write, and then there are techniques to go and write it as Boolean expressions and do several things with it. So this is a very useful skill. Start from a row which has a, so look at all the rows which have a 1, and wherever there is a 1, go and look at the corresponding left side and come up with a term like this which looks at the correct conditions which will make them a 1. So if the x1 is 0 and x2 is 0, the output must be 1, that is what this one captures, and so on. So this is the same thing that I used in the previous example. For XOR also I used the same trick. This is a slightly different example, that is all. So to implement this circuit, so it is a, we have the Boolean expression here, and we have 3 terms here, we need 3 AND gates for that, and we need to be able to combine 3 of these inputs using OR. So instead of using 2 input OR, I have used a 3 input OR gate here. A 3 input OR gate can take 3 inputs and the output will be 1 if, even if one of the inputs is 1. So even if one of these wires, if they have a 1, then the output will be a 1. The rest, these 2 inverters are just used to get these corresponding terms and so on. So if you look at the circuit carefully, you will realize that this term is capturing x1 and x2, so that is this. Then this one is capturing x1 complement and x2, and this one is capturing x1 complement and x2 complement, and these 3 are logically OR together to get your final output. So sometimes it is useful to go and simplify this. We will take the expression that we had earlier, x1 complement and x2 complement plus x1 complement and x2 plus x1 x2. So this is the expression that we had earlier. So now I am going to try and simplify this. It looks like it is a big expression, I am going to try and see if I can simplify it. So this is x1 complement and x2. I am going to take this term which is in the middle and make 2 copies of it. So I showed this earlier to you. I made 2 copies of this, and for this part x1 complement seems to be common, and for this part x2 seems to be common. Right. So once you have that, then we have x2 complement plus x2, that is the same as 1, x1 complement plus x1 is the same as 1. So, and we know x1 complement and 1 is x1 complement, 1 and x2 is x2. So this is a much simpler expression than what you have here. So the way to interpret this expression is, so you want to be able to sometimes read in English and understand whether what you have done is correct or not. Yes, I did start with this table here in slide 11. I started with this table here, but I want to be able to take this expression here and understand whether it is correct or not. So what does this expression say? Either x1 must be false or x2 must be true, right. So that is what this one says, either x1 must be false or x2 must be true. Let us go back and check the table. Wherever there is a 1, either x1 must be false or x2 must be true. So if I take this row, x1 is false, so this is a 1, in this row also x1 is false, so this is a 1, so this is okay. In these 2 rows x1 is false is not correct, so x1 is actually true in these 2 rows, however x2 is true only here, so that row gets a 1 and the other row gets a 0. So again x1 must be false is true for these 2 rows, so automatically they become a 1. x1 is false is not correct for these 2 rows, in this case we expect x2 to be 1 or true, and therefore only this row gets a 1, the other row gets a 0. So this is a fairly quick way to check whatever expression you have, is it what you want from there. So sometimes it is useful to think in English and go and justify that the Boolean expressions are correct or not. And once you have this, it is not just a mental exercise, it actually does something to the circuit. So what it did is, if we take x1 complement and or x2, now x1 complement requires 1 inverter and we have a logical OR here that requires 1 OR gate. So it looks like we use 1 OR gate and 1 inverter as opposed to the complicated circuit that we had earlier. So if I charge you, let us say 1 rupee for each of these gates, then you will pay me 2 rupees, one for the inverter and one for the OR gate here, whereas if you did not minimize, you have 2 inverters, 3 AND gates and 1 OR gate, you would have paid me 6 rupees for it. So in engineering, it is always about cost. Sometimes its cost is directly related to money. In this case, if I go and ask you to buy these components from a shop, if you did not minimize, you would have spent 6 rupees to do this circuit. If you minimized it, you would have spent only 2 rupees on the circuit. So it is good to think about whenever you want to minimize, you are actually cutting down the cost in some sense. In this case, it is the count of the number of gates. So I want to do a slight switch from the Boolean expressions and give a very simple description of what number system means, because this is useful in the later modules. So let us look at a decimal number like 756, right. So what do? We start with hundreds, tens and ones. We usually start from the, if I give you a bigger number, you do not start from the left side. If I give you 756, you can read it as 756. If I give you 7564, you may read it as 7564, but if I give you 10 digits, you do not usually start from the left side. Usually start from the right side. You say the rightmost digit is for ones, the next digit is for tens, then it is hundreds, thousands, 10,000s and so on, right. So if I give you this in the decimal system, we have the positions, and the positions come with certain weight. The position, the rightmost position has a weight of 10 power 0 or 1. The position slightly to the left of it has a weight of 10 power 1 or 10. The position to the left of that has a weight of 10 squared or 100 and so on. So if I actually want the value 756, right, so it is equivalent to 7 into 10 into 10 plus 5 into 10 plus 6 into 1. So that is what gives me 756. So this is a system where we have used 10 as the base. So the base is 10, which means the weights that we are using are all increasing powers of 10, starting with 10 power 0, going to 10 power 1, 10 power 2 and so on. If you had a decimal, let us say 756.4, then when you cross the dot, it actually goes as 10 power minus 1, 10 power minus 2 and so on down. The same thing can be done with so called binary numbers. If I give you a number 111, first of all a binary number can have only 0 or 1, it cannot have anything else. In this example, I have a binary number which has 3 ones, 111, and I want to be able to say what this binary number is equivalent in decimal. If I want to do that, if I want to find out the weight of the actual value of the binary number 111, just like what we had here, we assign a weight of 2 power 0 for the last bit, assign a weight for 2 power 1 here and assign a weight for 2 power 2 here. So the binary equivalent, the decimal equivalent of this is 2 squared into 1 plus 2 power 1 into 1 plus 2 power 0 into 1, that is what we have here. It is the same as 4 plus 2 plus 1, which is 7. So 111 written in binary is the same as decimal 7. So this is something that is very useful, we will need it in the next few modules and so on. So I have given a whole list of things. If you have so just like saying 4 digit numbers and 5 digit numbers and so on, we say 4 bit numbers here. So in this left side we have 4 bit numbers, and this lists all the combinations of these 4 bits can have. So 00000001 all the way up to 1111, and the notation here 2 is actually written as a subscript 0000 subscript 2, which means I want to interpret this number as a binary number. So 0000 base 2 is 0 into 2 power 3 plus 0 into 2 power 2 plus 0 into 2 power 1 plus 0 into 2 power 0, that is the same as 0. Let us look at this row here 1011, this is 1 into 2 power 3 which is 8 plus 0 into 2 squared which is 0 plus 1 into 2 power 1 which is 2 plus 1 into 2 power 0, which is the same as 8 plus 2 plus 1 which is 11. So we use the subscript to say that this is in a particular base. So for example, if I gave you something like this without the base, let us say I gave you 111 without the base, you may interpret it as number 111, whereas I really want to say it is the binary number 0111. So that is why we have this base explicitly here. 0111 base 2 is not the same as 111 because 111 is decimal 111. So we want to be able to distinguish these two. Same thing here, for example, if I gave you 11 here, if I didn't give the base, usually it's base 10, so this is number 11, but the same thing if I give 11 base 2, that will be 1 square 1 into 2 plus 1 into 1, which would be number 3. So this is something that's good to keep in mind. And if you want to go to from binary to decimal, all you have to do is start with 1 and go in multiples of 2, that gives you the weights. So in this case we have 4 numbers, you put 4 columns 1, 2, 4 and 8, so it starts with 1 and it goes in powers of 2 towards the left, and take the number, take the bit, multiply, take the number, multiply with the bit and so on, and add all of that up, that gives you in this case 13. Similarly here you have 128 plus 16 plus 8 plus 4 plus 1, that seems to be 157. So 1001, 1101 is actually the binary representation of number 157. In the later class we will see how to go from a decimal representation to a binary representation. This is something that you might have done in school, but I will give you a quick refresher in a separate module. So this brings me to the end of module 3. In this module we saw some basic Boolean theorems. We also saw various ways of explaining or simplifying expressions by using little tricks. I showed you how to take a description of a problem and come up with a circuit for that, and finally I showed you the number representation. So many of these skills are useful later. So what I would suggest is for you to go and review the material a few times so that you know exactly how to solve some of these problems which come up later. Thank you very much.